This video looks at transforming trig graphs. We'll look at combinations of transformations, and we'll also look at the order where it's important and look at the situations when it is important which order transformations take place. During the lesson on this, we'll have a look at the graphic display calculators and how we can use those to help us with these transformations. First, we'll look at the function y equals cos 2x. If we look at y equals cos x, the function y equals cos 2x is a stretch of the cos graph with a scale factor of 1/2. Remember, when it's in x, it's 1 over whatever the coefficient of x is. And it's parallel to the x-axis. So if we look at our cos graph that we're very familiar with, here starting at 0, 1 and then at 90 or pi over 2, we get a value of 0, at pi the value of -1 and so on. The effect of this stretch is to halve these x values. So for any given x value becomes half, and the graph looks like that. So we can see here that, for example, this minimum point here at pi is now at 1/2 pi. This point here has moved to here. This point here is moved here. So the distance from the y-axis is halved. Translations, well, if plus b comes after the function, it's a translation in the y direction. And here we've got a plus a, which is in with the x, and that's where we get a translation of minus a in the x direction. Remember, the sign changes. Remember back to the transformations we've done previously in Core 2. We talked about that slightly more difficult stretch when it's in with the x here, where it's in the x direction. This stretch is a bit easier. This is the y stretch when the whole function's being stretched. It's a bit easier to understand, to work out what's going on. Remembering that the x1 is where it's 1 over k when there's k in front of the x. Looking at reflections, well, the easiest one again is the one where it's y, and that's when we reflect in the x-axis. Every y value changes sign when we reflect in the x-axis. We're changing the value of the whole thing, in other words, what y equals. So if we reflect in the x-axis, we see where y is 1 here, it will become -1. And obviously these points here where y is 0 will still be there. And the red graph there goes to the blue graph there. This is of course the sine graph, and this is now minus sine x. This is the effect that reflecting in the x-axis has. It changes the sign of the whole function, in other words y. All the y values change sign. So in general terms, if we have a function of x, y equals a function of x, then a reflection in the x-axis, y equals minus a function of x. Reflection in the y-axis is a bit more complicated. What happens is every x value changes sign. If we reflect in the y-axis, whatever values of y we get for, say, x is -2, we will now get for x equals 2. So the effect is, if we have this function here, it goes to this function here, where you can see the only difference is everywhere we've got x, it becomes minus x. So in general, a reflection in the y-axis is given by a function of x becomes a function of minus x. Every x value turns to minus. So to summarise, reflection in the x-axis changes the sign of y, so the whole thing changes. Reflecting in the y-axis changes the sign of x. We'll have a quick look at some examples. If we start with the cos graph, we'll look at a stretch with a scale factor of 2 parallel to the x-axis, a transformation of 0, 2, in other words a transformation of plus 2 in y, and a reflection in the x-axis. We'll take it a step at a time. So first our stretch of 2 parallel to the x-axis. We'll take cos x to cos half x. Remember, when it's x, it's 1 over whatever the scale factor is. And this is what we start off with, and this is what we end up with. These distances are now doubled because of the half here. Remember, 1 over a half is 2, isn't it? Scale factor of 2 parallel to the x-axis. And you can see the doubling of the distances there. Okay, now our translation. Well, we've got to here, and this is the effect it will have. It will add 2 to the whole thing. It's y, it's the easy one if you like. We just stick it on the end. It doesn't interfere with this. We don't need brackets, but it's good practice. It helps to clarify what's going on. And this is the effect. This is our y equals cos half x graph that we've just got from that first stretch. And it simply adds 2 to all of the y values. And you can see there plus 2. And then finally our reflection in the x-axis. Well, here's the x-axis. That's going to work as a line of reflection. We're now on this graph here. It's minus the whole thing, because remember, when it reflects in the x-axis it's minus f of x, so it's minus everything we've got. We can expand that out, can't we? Multiply out by minus 1, and it gets us to this. And that's what it looks like. We now have the black curve, and job done. And you can see there how the points are reflected, these distances being the same. We have to be careful when we've got a stretch and a translation in the same direction. For example, a stretch with a scale factor of 3 parallel to the y-axis, followed by a translation of 0, 1, in other words plus 1 in the y direction, takes y equals sine x initially to y equals 3 sine x, and then to y equals 3 sine x plus 1. If we do the translation first, however, we get y equals sine x plus 1, and then the stretch, well, it's 3 times the whole thing, isn't it? So we get y equals 3 sine x plus 3. You see, they're not the same thing, they're different. So be very careful. If there's a translation and a stretch in the same direction, you must do it in the right order, the order that the question dictates.